Hey, our next talk is Santiago Bernal will give a presentation to uncover AGNs in low stellar mass galaxies.
Thank you. Thank you for the opportunity to present our work here. I'm a PhD student from the Universidad of Valparaíso in Chile, and I work with Dr. Pablo Sanchez Caradizo and with Dr. Patricia Arevalo, who is my supervisor. And so today I want to talk about why we want to find AGNs in low stellar mass galaxies. What was the selection process using the random forest classifier? How we do confirm these AGN candidates doing the spectral fitting, and which results we found. And if I have enough time, I would like to present a new tool that we are developing to help in the fitting process. So why low stellar mass galaxies? I think it was a big topic last week. I was not here last week, but there are many open questions about these objects. The occupation fraction, so how many AGNs are in the low stellar mass galaxies and how they are in the scaling relations, black hole mass and the stellar galaxy mass, because we need to fill still this gap here. And with that, also to see at the mass spectrum of black hole, we are looking for more intermediate mass black holes to see how many are there. And with that, we also are interested in the formation and evolution of supermassive black holes. So because the seeds of these supermassive black holes are in intermediate mass black holes that we can find at high redshift, but not easy to observe them. So we can use black holes in low stellar mass galaxies or a low redshift and to study as a similar. So there are many questions. And to answer that questions, we need to find these agents in these low stellar mass galaxies. And for that, we started with CTF photometry data, that is a photometry survey on the optical bands with a cadence of 3 days. And here is an example of a science image that we can have from CTF. And because of that cadence, we can construct a light curve. So this is an example of a light curve from one of our candidates. And what we are looking here is the variability and other properties from this object, but the variability that we can observe in these light curves. However, the sky is full of variable objects. So we have, for example, supernovas, we have stellar objects like Cepheids or cataclysmic variables, and we are interested on quasars, AGNs, or blazars. Yeah. So we need to try to find only these ones. And for that, we can use different data products from CTF. One is called the alert stream, which is a photometry over difference images. The difference images, basically when we have a new observation, a new science image, is compared with the template image, and then we obtain the difference image in that plot. And the photometry is over this one. But this is produced only when the difference is at least 5 sigma. So what happens is that the light curve is not going to have all the observations, only when alert is triggered. They happen.
Disconnected.
Yeah, out of the session. Trying to reconnect.
It could be the it is it has been. So let's see if you maybe yes. Yeah, you're seeing. Turn it off. Looks like it's back. Second. Okay. Yeah. Let's see if we can. Did you roam?
Not really.
And is there an online version of your talk anywhere?
Just yeah.
Just like, so is there an online like URI, use my computer or something like that?
Yeah.
Okay. You want to try?
Right. Now I'm back.
Okay,
So this-
let's try again. Okay. There you go.
Okay, sorry for the interruption. So I was talking about the different CTF data products. So we already talked about the alert stream, and yeah, the live course from the alert stream are not complete live course because it's only triggered when we have these 5 sigma detections. Then we have the data release that is PSF photometry, but now over the science image. And here we can have some problems for the extended objects. So errors that are not well estimated, and that can introduce variability in the live course. And we have the force photometry live course that is PSF photometry over all the different images. So it's going to be a complete live course and without the problems for the extended objects. So best quality live course and with better errors. And so we use a classifier for these different data products. Here is the schema of the random forest classifier for the alerts live course. And one thing that I'd like to highlight about this classifier is that we are not using just the class no AGN and AGN. So here are different classes, and we are interested in the, sorry. I'll try to do this.
No.
Okay, so this is the tree structure for this classifier, and similar for the live course of the data release and the first photometry. So we have different classes, and we are interested in the ones that are AGNs. And now that we have the candidates, we go to the confirmation using the spectroscopic data. So from the model of AGNs, when we observe on the optical range, we can observe the emission of these broad emission lines. So here in particular, H alpha and H beta emission lines that are broad, and we can say that if we detect broad emission from the sources, we confirm an AGN. So we do that using PPXF for fitting the spectra. We use a complete set of templates, which means that we are using stellar populations, emission lines for the narrow region and the broad region. We also have the high order emission of the Balmer lines, the Balmer continuum, the pseudo continuum of iron 2, and power loss for the AGN continuum. So we can decompose the spectra. Sorry.
Sorts of technical issues.
Yeah,
Me too.
just playing with me there.
Yeah,
Okay. Have to show. Oh, yeah. So from here, from this fitting, we can extract the flux of the different emission lines, the different components, and also the kinematics. So to perform later further calculations. So now let's go to the results. So as I mentioned, we use the here.
Is it okay?
Yeah. No.
There you go.
There's a lag
I was
between
having all sorts.
my.
Yeah,
Yeah.
it was not advancing for me this morning. So you're doing great.
So we use the CTF photometry data products, the classifiers, and then we cross-match our candidates with the NASA's Long Atlas catalog to search for low stellar mass galaxies with a mass limit of 2 times 10 to the 10 solar masses. And the redshift limit is 0.15. This limit comes from the catalog. Here is the distribution in the sky of the candidates for the different sets, different colors for different sets. And the total candidates, unique candidates, are 506. And we have different numbers for the different sets. And that's because one candidate can be in more than one set. Because we have alerts or data release and force photometry for the same candidate, so it can be on different sets. Then we look for spectroscopic data on the SDSS archival. So here is the distribution of candidates with spectra in blue and without spectra in orange. And we found 454 candidates with spectra, but we did a good on the quality of the spectra and also some sources with bad estimation of redshift. So probably bad estimation of the stellar mass. Then we take out the objects, and at the end we have 415 candidates with good spectra. And here's the redshift distribution for that candidate. Then using the fitting, we look for the broad emission lines, and we put as a condition that the equivalent width of the broad emission lines to be higher than 5 angstroms to say that we detect broad emission, and we confirm as an AGN. So we found that for 86% or 86% of our candidates, and here's the distribution for each set. So one thing that we notice here is that the ones that doesn't show the equivalent width higher than 5 angstroms are coming from the alert set. So maybe expected because we have no complete life curves and can be more less clean selection in that sense. Then we estimate the mass of these objects using one-epoch relations. So here's the distribution for that masses. Here's the mean values for the different sets. It was around 2 times 10 to the 7 solar masses. And here we notice that for the first photometry set, here in blue, we have more objects with the lower mass. So one of our conclusions is that the first photometry is more sensible to these lower black hole mass objects. We also look for the ratio between the stellar mass and the black hole mass. So the ratio is around 1,000 here, the distribution for all the objects. And again, the first photometry showing more objects on the, in this case, for the higher ratio values. That implies the same that we're looking lower mass black holes in this set. And here is the relation between the black hole mass and the stellar mass. In blue are our results. We overplot the Raynes voluntary in gray, and with the dashed line, the relation that they found. And the purple line, the expected relation from larger mass black holes. So our data is more aligned with that, with what we expect from larger stellar mass galaxies. But however, is that maybe we are just more sensible to larger mass of black holes with this method. And maybe we need a better data to go deep in magnitude to observe objects with lower
Take your
mass
time
black holes.
bringing it back. We definitely want to see the results. They're great.
Yeah, and we also use the flux ratio between narrow emission lines for the VPT diagrams. And here in color are all the objects for the ones we detect broad emission line. And the color bar is the mass. We try to look for a relation between the class on the VPT diagrams and the mass of the objects, but there is a small difference, but no clear trend between different classes. So we also plot here the objects without broad emission lines. Almost all of them are on the star forming class on the VPT diagrams, only 5 without broad emission lines that are classified as safer. And here is one particular, it's the green square that also have an X-ray contrapart. So we look for the X-ray contraparts of these candidates using the one catalog. And here is the equivalent with distribution of the candidates that are 195 on this region of the sky. In orange are all the candidates. In blue, the ones with X-ray contrapart. Here is the one that I mentioned before without broad emission line and with cipher classification on the VPT diagrams. And here in red are also candidates with broad emission lines that are classified as star forming and that have X-ray contrapart. So they are in all that classes. And in this Venn diagram, we show the different classes of X-ray contraparts when are classified as AGN on the VPT diagrams and when they show broad emission lines. So 43.6% of these candidates are classified as AGN by the X-ray detection, the VPT class, and the broad emission detection. An extra near 23% have X-ray contrapart and broad emission. And they only one object with X-ray contrapart and AGN VPT classification without broad emission. And we have only 11.8% that are the ones without H alpha equivalent width enough to say that we detect broad emission lines. So here, 0% shows that there is no one candidate showing only X-ray emission that is not classified as AGN by the broad emission lines or by the AGN class in the VPT diagrams. So the percentage in total with contrapart is 67%, which is let me say a higher percentage compared with previous works that use variability to select AGN candidates in low stellar mass galaxies. So it's just my summary and conclusions. So we use the plan to show.
Yeah, you have plenty of time. You're right. I wouldn't even give you the 5-minute warning yet.
Yeah,
Like,
okay.
you didn't have problems. So you have,
Yeah, I'm out again.
and it's not advancing.
Okay, just summary, we use the CTF photometry data and we can use for the future the LSD data and it's going to be larger number of objects and also more deep observations. So we are going to be able to detect more objects with this method.
You can put up your conclusions.
Yeah, it's trying to.
Yeah.
And so we found that 86% of the candidates show a broad emission line. So it's for that reason we call it a successful detection of AGNs using this method. We also observed that using different data products from CTF can give us maybe a different range of values on the black hole mass. And in particular, when we have the force photometry life curves that are better life curves and complete life curves, we are able to detect more objects with a lower black hole mass. And a conclusion about the VPT diagrams, that they are the ones with broad emission lines are in all the classes. So sometimes people use the VPT diagrams to select candidates, and it's not working for all the candidates. So I think you discussed that last week. And also, as I said, we detect 60% of the candidates in the Eurosita D sky with X-ray counterparts. So I think I finished here and happy to give you questions. Thanks.
Mentioned that you need longer light curves, more complete to really be more efficient.
Yes.
LSST is just going to be starting soon, so it's not going to be complete. How long of a baseline do you think you need?
Well,
You have several bands.
Yeah, so the idea to have more complete is to ensure the variability at different time scales. So depending on what we are looking, if we're looking at long time variability time scales, we're going to need more observations from LSST. But for the ones that we expect a time scale smaller, like the ones with low mass, we can use like 1 year maybe be good for them. Yes.
The 67% have Eurosita X-ray detections, right?
Yes.
Like, why is that higher than other surveys? Is it better coverage or?
I think that's a matter of how they were selected and how deep the observations are in both sides, the optical and the X-ray. So maybe there are more X-ray counterparts, but we need deep observations on the X-rays. Yeah, that's the difference.
Okay. Yeah. Like, what does that compare to, like Rosat survey before?
Well, we did a comparison with other works that select AGN candidates in low stellar mass galaxies using variability. And I think the higher percentage for one work was 6% the candidates. But yeah, it's a matter of the observation constraints.
Well, Varda has a question.
Yeah, I think.
Yeah, thank you, Santiago. Really nice talk and impressive results. I was wondering, those objects that in the BPT diagram are not AGNs, they could still be AGNs, just that, of course, you have an integrated fiber. And so they might fall in the star formation region just because they have a lot of star formation in the outer parts, but it doesn't mean that they couldn't still be AGN, right?
Yeah, that's that. We cannot confirm with the data that we have, but we can look for IFU observations for that objects.
Yeah.
I'll say the same thing. The notion of yes and no AGN I still find difficult. AGNs with accretion rate of 10 to the -6 to maybe 1. So it's not yes or no AGN. It's basically what fraction total flux do we see coming out from the center black hole with galaxy. And that number will probably, if you have good enough measurements, never be 0 for any galaxy.
Yeah,
So saying it's an AGN or not, we need to be very careful with you.
yeah, yeah.
My question was about the environment. I don't know whether you mentioned this and I missed it. Some things are relatively nice, large. We had brief discussions last week on, whether we are biased towards the kind of smaller galaxies that, smaller close AGNs that we see, what environments they might be in, whether you would have any plans to interface perhaps?
No, not really. We select candidates from all the CTF survey type, no particular regions, but go through
Clusters,
Yes.
what sort of companions do these things have, and whether there are any trends in there?
Yeah.
I was wondering if there was any overlap between the new sources that you discovered, variability with radio sources that have been reported in the past few years that have a radio, possibly a radio called AGN. Seems like you haven't.
Yeah. You can see them going to say we didn't check that, but possible to do.
I think, a bit controversial. I was wondering if any of them are variable, as you did.
Last results, suddenly found things that.
Yeah. Yeah.